This video clip will take a look at hybrid orbital geometry and VSEPR, which is known as the valence shell electron pair repulsion theory. First, let's step back for a moment, just revisit our hybrid orbitals. We have our 5 hybrid orbitals ranging from sp to the sp3d2. The hybrid orbital scheme is figured based on the number of equivalent orbitals we need in our molecule. For example, the sp gives us 2 equivalent orbitals. sp3 provides 4 equivalent orbitals. The sp3d2 provides 6 equivalent orbitals for our molecular structure. In our hybrid orbital scheme, each one of the orbitals that we have in the hybrid orbital bonding scheme can hold 2 electrons when creating a molecule. So in every orbital, whether it's sp with 2, sp3 with 4, or sp3d2 with 6 equivalent orbitals, each orbital has the capacity to hold 2 electrons. Another concept key to what we'll be taking a look at is that the hybrid orbitals are only the valence orbitals of an atom. Underlying orbitals do not participate in the hybrid orbital scheme. It's only the bonding electrons or valence electrons that require the use of hybrid orbital. Now, as we take a look at what's called the geometry of the hybrid orbitals, the 3-dimensional spacing of the hybrid orbitals is determined by something known as VSEPR, or the valence shell electron pair repulsion theory. Run through that again. What the VSEPR stands for is the V is for valence, the S stands for shell, the E electron, the P pair, and then R repulsion. And this is all a theory. Now, valence shell electron pair repulsion theory sounds rather highfalutin, but essentially all it's telling us is that a pair of electrons in an orbital will repel another pair of electrons that are in another orbital. And they do this to get their maximum separation from one another. For example, let's consider the sp hybrid scheme. The sp hybrid scheme creates 2 equivalent orbitals. Each equivalent orbital can hold a pair of electrons. So we have a pair of electrons in one orbital, a pair of electrons in another one. These pairs of electrons will have a repulsive force on one another, pushing each pair as far apart as possible, and once they have maximum separation, that determines the orbital geometry. In this picture, the pairs of orbitals are only 90 degrees apart. They can push each other further apart to get more separation. That will determine our geometry. For sp, once the orbitals have pushed each other such that they're each 180 degrees apart from one another, the orbitals are now at maximum separation possible, and that determines our orbital geometry. For sp, we describe our orbital geometry with the orbitals 180 degrees apart from one another. This would be known as a geometry as linear. That would be our orbital geometry. If we look at sp2, sp2 hybridization gives us 3 equivalent orbitals. The pairs of electrons will repel each other to get maximum separation. So in this case, these orbitals will move up slightly to move a little further away from the orbital on the bottom. Once maximum separation is achieved, that's the orbital geometry. Our 3 orbitals reach maximum separation when the angle separating each orbital is 120 degrees. This particular geometry is something known as trigonal planar. It's 3-sided, trigonal, and the shape is it's flat. The sp3 hybrid scheme, we have 4 orbitals, each containing a pair of electrons. Those pair of electrons, valence shell electron pair repulsion theory, will repel each other, push each other apart, and the angle of separation between all the 4 orbitals is 109.5 degrees. And the geometry for sp3 hybridized orbitals is something known as tetrahedral. Looking at all the orbital geometries, once again, maximum separation of the orbitals so that electron pairs in each orbital can repel each other as far apart as possible is a determining factor in the geometry. Our SP, we have a linear geometry, SP2 trigonal planar, SP3 maximum separation is tetrahedral. We get to SP3D, we get the trigonal bipyramidal orbital geometry, and for 6 orbitals to get maximum separation, the orbital geometry is known as octahedral. Let's do an example of how we'd use this information. Let's start out with the molecule ammonia, NH3. Looking at our Lewis structure of NH3, we have one atom, we have an unshared pair for 2 things, another atom for 3, and then another atom for 4 things around our central atom. Number of things tells us how many equivalent orbitals we need. Number of equivalent orbitals is 4. 4 equivalent orbitals is provided by sp3 hybridization. To provide 4 orbitals maximum separation, where each pair of electrons in an orbital repels a neighboring pair of electrons in another orbital in our hybrid scheme, 4 orbitals equally repelling from one another gives us an orbital geometry known as tetrahedral.